Hi, and welcome to this presentation about Greybox modeling. I am Ole Magnus Brastein, and I did my PhD on specifically Greybox modeling framework a couple of years ago. So naturally this is a topic that I am very interested in, and I guess you are too, since you are here listening to me talk about it. The agenda for this presentation is first going to be to give some background into the idea of Greybox modeling, what this is actually all about, what do we mean by a Greybox model. I will discuss some different types and definitions of Greybox models, because there are several points of view on what should constitute a Greybox model out there in the literature. Then I will define more specifically what I mean by the Greybox modeling framework, which is what I did my academic work in. Then I will continue a bit on discussing the general concept of fitting models to data and how we actually can do that in a mathematical, rigorous way, which of course is very closely related to the Greybox modeling framework. For the second part of this video, I will be discussing different formulations of the so-called state filtering problem and how that relates to Greybox modeling framework. And of course then the specific implementations of the state filter, which is linear and nonlinear Kalman filter versions, including the Ensemble Kalman Filter and also the so-called particle filter. So first of all, this very common engineering task of building models of dynamic systems can be approached in many different ways. The most sort of obvious and first experience most engineers have with the models is what we call a white box model. That is some type of model which is based on human expert knowledge, meaning somebody who is an expert in some field, who understands the physics of a particular process, writes down the equations that governs this process using physics or chemistry equations, and tries to explain the process. Typically this is based on so-called first principles like balance equations, mass and energy balance. You could argue that the laws of physics themselves are a sort of white box model of the real world of nature. So it's some sort of mathematical representation of the underlying physical phenomena that governs whatever process we are interested in studying. The advantage of this form of model is that the physical equations, since they are written by a human, tend to be interpretable, meaning that another expert of the field can read your model equations and understand the underlying process. So it's a way of communicating your knowledge in a way that can be understood by others, in addition, of course, to implementing this model equations into a computer for purpose of simulation. Another advantage of this white box framework is that it tends to generalize well, meaning that if you develop your white box model, you typically do it based on the understanding of a particular type of process, not necessarily an exact implementation of a process. So for example, in the oil industry, you're not developing models for a specific well, but you're developing models for wells in general. And then you can sort of, by adjusting parameters, you can make it fit a particular well. But the models themselves are developed based on general principles and general understandings of sort of a whole class of processes and not one specific instance of such process. In the sort of complete other end of this white to black box spectra, which we have up here, we find this so-called black box modeling paradigm. And this is a completely different approach to doing dynamic system models, where rather than modeling based on human expert knowledge, we are now using so-called empirical knowledge, meaning knowledge of the process of interest which exists in the data we have. That's what empirical means. And the way to do black box modeling is that we have some sort of general mathematical model structure which we calibrate using this data. And out of this process, we can develop a dynamic system model, which is then tailored to a specific process. And since we are here using like a general mathematical structure. Let's say neural network could be an Armax model, subspace system identification. There's a lot of different versions of this. But all of these methods are based on mathematical structures that are sort of general. They're not built to fit a particular system. So when you calibrate them, all of the information about your particular process is hidden in the parameters of that structure, which makes them somewhat hard to analyze. You cannot just give a neural network to another expert in some field and expect him to understand the underlying process. That's very, very difficult to do. But the benefit of this is that since these models are calibrated to fit a particular system, they do tend to provide very good prediction accuracy because they are made for a specific instance of the system and they are not generalized in the way that white box models are. And also the calibration process tends to provide more statistical information about just how good this model is to fit your particular system. Since we have data, we have some information of a specific instance of a system, and the calibration process on that data can give us some insight into how good the final model actually is. So then we have, on one end of the spectra, we have the white box model, and all the way over here, we have the black box model. And we see from the headings here that the black box model uses, in principle, no physical information, whereas the white box model is based entirely on physical information. And in terms of parameter calibration, the pure white box model has no need for calibration because all of the parameters are given by the physics of the system. Whereas in the black box case over here, calibration is sort of all we have. The entire structure of the model is just some general mathematical expression, and it's the calibration process that makes that general mathematical formulation actually do something useful. So in this context then, what is actually a Greybox model? Well, it turns out that it would be very interesting if we can somehow combine the benefits of white box and black box model here. And Greybox models are the attempts to actually do that. So what we want to do is we want to combine physical knowledge, modeling knowledge, physical knowledge of the underlying process with measurements or with data from that process. And this results in a model structure that is partially based on physics, which also has some sort of softness to it. It has some parameters that are undetermined by the physics, which instead is determined through calibration against a specific set of data. And if we do this in a clever way, we can obtain the benefits of having both prior physical information, like the white box model, which helps with generalization and interpretability, and we can have the benefit of good accuracy because we have some parameters that can be calibrated to a particular system. And it turns out also that in engineering, it's almost always the case that we do have some prior physical knowledge that we could, with advantage, utilize. It's almost never the case that we are completely in the dark and that we only have a bunch of measurements and no idea about how the underlying process actually behaves. So it's very interesting to develop frameworks that are able to utilize both prior physical knowledge and data. And in fact, it has been claimed that this Greybox modeling approach is really a natural framework for dynamic system modeling. This discussion can be taken sort of one step further if you look at what we tend to do in practice, which is that almost all white box models do have some sort of parameters that needs to be adjusted. And almost all black box models have some kind of utilization of prior physical knowledge. So it could be argued actually that all models are in some sense gray, and that the idea of a pure white or pure black box model is just sort of an idealized extreme case which doesn't really happen in reality. It's always somewhere in between here. And this realization actually makes the study of Greybox models even more interesting because it helps us to develop a framework that can improve sort of all approaches to modeling by taking this into account. So first, some different types and definitions of what we could call a Greybox model. So one approach would be to have some sort of black box approach, but where we attach some sort of physically determined constraints on the parameters. An example of this could be, let's say, some kind of system identification approach, where based on prior physical knowledge, we know approximately the range of what the eigenvalues of the system transition matrix should be. So we might wish to constrain the approach to limit the eigenvalues of A into a space where we know that they are physically reasonable. That would, in a sense, combine physical knowledge and calibration, and therefore could be arguably placed inside this Greybox paradigm. Another approach, which in the literature is sometimes called semi-physical modeling, would be utilizing some sort of physically determined pre-processing. That is, based on our data, we use some sort of pre-processing technique, which we know from using prior physical information is reasonable for our particular system. And this is something which is very common in, for example, PLSR, where you can use, let's say, exponential transforms or something on your data, because you know that the eventual system behaves sort of exponentially, or like an exponential function. So by utilizing this sort of transformations based on physical understanding of this problem you are studying, you are kind of shifting this PLSR, which is a pure black box technique, into sort of gray, or at least dark gray area. A third approach, which can also be considered a gray box model, is if we have a literal combination of two model structure, one which is purely white and one which is purely black. This is sometimes referred to as hybrid models, especially in the machine learning world. And you can do this in several different ways. Over here we have an example of a black box and a white box model, which are connected in parallel. So both of them observes the real world, and then their output predictions is combined in some way. And this combined output can then be used as calibration information on a specific data set in order to tune this black box model. So the white box model would be unaffected by calibration, but the black box model would be affected by calibration. But the white box model is then contributing to explain some of the data. So some of the relationship from input to output would be handled by the white box part, but anything which isn't handled by the white box part would then through calibration be handled by the black box part. So you can sort of augment your white box model with some additional black box state equations, for example, in order to improve your overall prediction capability. And a similar approach to this would be to connect black box and white box models in series, where the output of the black box model is given as an input to the white box model. And this would be an example where we use the black box model to try to model some part of the system which we are not able to describe in physics. So some part of the system might be too complicated or unknown so that we cannot actually develop a white box model for it. But then we could model that as a black box system, and then feed the output of the black box system as an input to the white box model. And then again, this overall system is calibrated by adjusting the parameters of the black box structure over here in order to give us maximum fit with the data. And the final way of doing this is also a series connection, but this time with the white box model first. So that would mean that the white box model tries to predict the information in the data, and then the black box model learns from the prediction errors of the white box model in order to give better predictions. So then the black box model uses the white box model's predictions as an input and learns based on the data input how to better predict the overall output. So this is also a series connection, but now it's sort of trying to learn from the residual errors of the white box model if there is any sort of residual structure left in the white box model output versus data, then the black box model can compensate for that. The final example of a gray box model, which is the sort of definition that I will be talking about in the remainder of this video, is what we call simplified physical model structures, or mechanistic models here. So this is a framework where we try to do some sort of simplified white box models. We are not really seeking a complex white box model structure, which is an exact representation of the system, but we are looking for something which is an approximation. And typically this constitutes some sort of lumped parameter approach. So we have a very simple description of the system. For example, let's say the thermal behavior of a building could be represented so all of the walls of the building could be represented by a single thermal resistance, for example. That would be a very gross simplification of the real system, which is a very complex interconnection of different materials and structures. So representing all of that by a single parameter is clearly a simplification, and it constitutes a lumped parameter approach. And these lumped parameters are in general not possible to compute by hand because it's too difficult. It requires too much detailed information. So in the Greybox framework then, we develop these simplified models, and then we calibrate these unknown parameters using a set of data. So that's where the gray part comes in. Simplified model structure plus data equals Greybox modeling framework. And this has the advantage that if this is done according to a strict mathematical scheme, we can do this in a sort of iterative way. So we start with the simplest possible physical model that we are interested in, and then we can calibrate it. And then through statistics, we can actually test if this model is adequate for explaining the data we have. And then we can keep increasing model complexity in this sort of iterative construction and validation scheme until we have a structure which is exactly sufficient to explain the data, but not more complex than what it needs to be. And this has advantages in terms of this data-driven problem of overfitting models. So models that are too complex and therefore lose prediction accuracy to overfitting. In the limit case, you can consider like standard white box physical models, which has some few unknown parameters, often called like fudging factors, and some parameter that we include in the model as a tuning parameter in order to help fit models to real physical system. This is also kind of an example of this, but in a sort of a very limited case, what Wernholt and Moberg called the lightest shade of gray. So then a definition of the Greybox modeling framework, which I will be talking about for the rest of this presentation. By Greybox modeling framework, we will understand the estimation of unknown parameters in a known model structure that has in some way been partially derived from prior physical knowledge. And the key here is that by realizing that, of course, data is uncertain. This is fairly well understood, I guess, by everyone in engineering, that we always have measurement noise in data. So we never trust data exactly. We always assume that there's going to be noise and inaccuracies in data. But since we are now dealing with simplified models, we also have to account for the fact that models are an approximation of the real world. That's of course always true, but we tend in engineering to think that our models can somehow exactly predict the real world, which is of course not true. Models are always simplifications, but in this case they are very strong simplifications, which forces us to account for the uncertainty in model predictions as well as in the data. And in the Greybox modeling framework, that is sort of the key to success, is how do we actually balance the uncertainty in the model versus the uncertainty in the data. And I will focus on offline methods for doing this, or batch methods. There are also online approaches to this, that is sort of methods which estimates the parameters in real time. But for this presentation, it's going to be focusing on how to do this in offline or batch modes. First, some nomenclature and definitions to help make sense of the equations to come. The first thing we need is a data set, which is a sequence of measurements. And we're going to denominate that as y of n in square brackets, where this square brackets is used to mean an ordered sequence. So from y0, y1 up to yn. That's going to be our definition for a data set. We also need a set of parameters, which is the free parameters of the model structure that we are trying to find. This parameter vector is defined as theta, theta 1, 2, and up to n theta, which is the dimension of this theta vector, so the number of free parameters that we want to calibrate. And since we are going to do calibration, we need some sort of mathematical expression of the goodness of fit, how good is a particular parameter vector. And for that purpose, we will use this symbol J here. So J of theta and a data set, that's some kind of numerical representation of how good this theta is to explain the observed data that we have here. And in order to find the best parameter vector, we can use sort of a argmax approach where we're trying to find the theta which maximizes this objective function. So the theta that gives us the maximum fit to data is going to be our best guess theta over here. One example of an objective function, which will be very important for the Greybox modeling framework, is this likelihood function over here. So by setting this J function equal to the likelihood, which is by definition the probability of observing the sequence of measurements, our data set that we have, given a particular parameter vector. This probabilistic notation of a vertical bar means that we assume theta is known. What then is the probability of getting the sequence of measurements that we have? And then, of course, we use this argmax approach or numerical optimization approach to find the theta which gives us this maximum probability of observing the measurements we have. And that's going to be then our best guess parameter vector. This is, of course, the maximum likelihood approach to parameter estimation. We also, of course, need a definition of a model, which we are just going to use sort of a standard state space representation, where we have the state transition F and the measurement equation G. And we have this uncertainty or noise component W for the process noise in F and V for the measurement noise in the G transition. It's a standard state space representation. So, before we get into the interesting world of state filtering, first I want to say something general about fitting a model to measurements or calibrating parameters. Because there are several approaches to this, and very often in engineering, when people do parameter calibration, they just do the approach that they learned in university or in the workplace, and not really think about what this approach is actually, what are the underlying assumptions of these approaches. So one very common approach to parameter estimation is doing what we will call ballistic simulation, which means you run your model over a data set and simulate the entire state development over a particular data set. And then after this simulation has been completed, we then calculate the errors between the resulting simulation and the collected data. So that's what we have here, where you see the state transition is a smooth plot. It's a smooth time series of data, implying that this has been just simulated all the way through using some model. And then after the simulation is complete, we calculate the differences between measurements and simulation and do some sort of mean square error maybe. Now, it can be shown that this approach actually assumes that the model is perfect. So we put all of the uncertainty on the measurements and none of the uncertainty on the model. This can be seen later when we look at the actual Greybox framework, why this is so. But intuitively, if we at every state or every time step of our simulation base the next time step only on the previous simulation, that implies that we trust the previous simulation, which is sort of what justification for this statement here, that doing this ballistic approach and then subsequent error computation after the simulation is complete implies that we assume a perfect model and all uncertainty on the measurements, which is of course not really realistic. We know that from engineering all models are wrong, but in some cases it can be still an adequate approach. I mean, this is a very common thing to do, and it clearly works, otherwise we wouldn't be doing it. So for many cases, this is an acceptable simplification to assume perfect model. Another completely opposite approach to doing parameter calibration is the sort of typical ordinary least squares approach to fitting data, where we actually do one step ahead predictions. So at every step, we calculate a state vector, and then we do a prediction to the next step, and then we do the error, but then we go to the measurements again to compute the states, and then we do another prediction from the measurements, and then one step ahead further. So at each step, we trust the data completely, and then we assume that all of the error is on the model instead. So at every step, we do a prediction one time step forward, and then we compare that to the measurements. But then before we do another prediction, we adjust completely to the measurements. So we always go from measurement to next step. That's sort of an ordinary least squares thing we do maybe in Armax models, typically something similar to this. So that is a completely opposite approach, where we actually trust the measurements completely, and we place all of the uncertainty on the model. And in many black box scenarios, this makes a lot of sense, because we know that the model, before we start calibration, we know that the model is complete gibberish. It's just some general mathematical structure with randomized parameters. So we expect the model to be completely wrong. And until we have calibrated the model, we don't really have any good idea about what the measurements should have been. So it's then sort of reasonable to just say, okay, we trust the data completely, and we assume that all the errors is on the model. Whereas this is typical of the white box paradigm, where we are trying to build the model the best we can. We put all of our own physical knowledge into the model formulation, and therefore it's natural that we actually trust the model completely and assume that it's the data that's wrong. However, if we wanted to do this in a more mathematical, rigorous way, which respects the fact that it's going to be errors on both model and measurements, as is the case for the Greybox modeling framework, then what we could do is use something that we will call the filtered state trajectory. So at every step, we will still do this prediction from one time step here to another, but then at the end of that prediction, we will, instead of adjusting completely to the measurements like we did here, we will adjust partially to the measurements. So it means we are actually saying that we use our model to make a prediction, and then we assume that that prediction is not going to be perfect, but neither the data is perfect. So we need to balance how much of the information in the data we use to adjust our state vector at each time step. And the whole key to this is actually figuring out how can we do this balancing? How can we balance the model and the measurement uncertainties in order to obtain a reasonable filtered state trajectory? And what we actually do here is we are not fitting the model predictions directly, but we are fitting the filtered state trajectory. So we are looking for parameters that gives us a filtered state trajectory that is in some way reasonable. And as we will see, this process of doing state filtering has some nice mathematical properties, which can help us to do a better job of fitting models to data. So we introduced in the previous slide this idea of filtered state trajectory. So we should then talk a bit about this concept of state filtering. So we could say that state filtering is trying to answer the question, what is the state at time k, given measurements up to and including time k. And this is clearly a stochastic formulation. We, in state filtering, give up on the idea that we can compute sort of an exact representation of the state. So in a general formulation, we use probability, and in other formulations, we use some other expression of uncertainty. But the key here is to understand that there is no exact formulation. We are looking for some kind of description of the time evolution of our state in the model that represents the uncertainty at each time step. In Jastrzębski, this is known as obtaining the filtering densities. That's, of course, then in the probabilistic terms. We can also say that the state estimation can be given at other times. So we can have something called smoothing, which is when we are looking also at future data. So that would be some sort of non-causal formulation. Or we can do prediction, which is then we are trying to find a filtered state somewhere in the future. So we are looking for some state using measurements yk, which then has some state in the future with respect to k. So if you are looking for the state at time k plus l, we call it prediction. But if you are looking for the state at k minus l, then we call it smoothing. So with respect to measurements at time k, then state at k minus l would actually then use measurements that is ahead in time, whereas this one would then trying to find the state estimate ahead of the measurements again. But for this one, we are, for the purpose of this presentation, we are interested in this state filtering formulation up here. I will focus on recursive methods for discretely observed systems, because those are the most typical used for parameter estimation. And this approach can be formulated as a two-step procedure where we have a predict and an update step. And in the general probabilistic formulation, this is known as a recursive base filter. And the idea is that we have our model here, and then we do a prediction using this model to get a new state, which we will call the a priori state. And then we use measurements here to do an update to get the a posteriori state. And then from the a posteriori state, we do another prediction to get a new a priori state in the next time step. And then we update that using measurements from that time step in order to come back to another prediction step in yet another time step. So this recursion here, that's what helps us to do this parameter estimation in a mathematically rigorous way. So let's look at an example of state filtering. And to demonstrate this, I invented an example with a robot, which is walking around in the real world. And it has a laser rangefinder, so it can make some measurements to an imaginary wall over here. So you can measure the distance to this wall, and then based on that measurement, this robot will try to figure out its location in the real world. So to start with, we are now at time step k minus 1, and the robot has some notion of its position, which is expressed as a probability distribution, that is, the distribution over the state at time k minus 1, given measurements up to and including time k minus 1. So this could be the initial state, which is then based on some prior information, or it could be the result of previous this recursion, so previous iterations of the state filter. But let's just say for purpose of explanation that we are now at time k minus 1, and we have this here, which is then the a posteriori distribution of the state from the time step k minus 1. And then from this time step k minus 1, we wish to propagate our system forward in time to time step k. And to do that, we use our model to come up with this blue distribution, which notice now that we are looking at the probability distribution for state xk. We are no longer at time k minus 1. Now it's the state at time k instead. But we are still using the same measurements. We're still using measurements up to time k minus 1 and not k. And when we do this prediction, that is, we propagate our probabilistic state distribution forward in time, it's natural to assume that this new state distribution will be more uncertain, because we are using an imperfect model. We are using a model which has uncertainties in it in order to propagate our system forward. So As expected, this probability distribution is wider than where we started, which indicates that we are more unsure about our position after we have performed this prediction step. And the prediction step itself up here is implemented or expressed as a marginal distribution. So for all possible previous states at time k minus 1, we integrate out the state, and we are left with this expression here, which is then the distribution over the new state at time k, but still keeping the measurement information the same. And then the next step here is doing a measurement update, which is now we wish to incorporate some new information. This measurement update is actually implemented or expressed using the very familiar Bayes theorem. So we are saying that given this here, which is then the prior distribution, that is the distribution before we include measurements, we can, using this equation here, we can calculate what happens when we add one more measurement. So what is then our new distribution of state using one additional measurement from the current time step k? And to do that, we use Bayes theorem, where we have the prior distribution as our prior, and then we include the measurements as the likelihood function, and then we have the so-called evidence term under here, which we will see is important actually for Greybox formulation. So in the plots over here, we have the measurements like this. That would be the G equation, which we use to calculate the measurement. And then we end up here with the new posterior distribution. So from the previous state distribution to the new state distribution through the prior distribution using the measurement information as such. Now, what does this all have to do with Greybox parameter estimation? Well, it turns out that this likelihood objective function, which we introduced in the previous slide, can be expressed by multiplication of partial densities like this. So using some probabilistic or statistical mathematical trickery, we can show that this likelihood function can be expressed on a multiplicative form as such. And this expression here is then calculated at every step when we do this state filtering process. And this expression here is actually the evidence term from the equation up here. So in the process of doing this whole iterative predict update state filtering scheme in a recursive Bayes filter, we actually calculate at every time step exactly this evidence factor which we need in order to compute the likelihood function over the parameters. So computing the likelihood function for purpose of doing Greybox parameter estimation can actually be implemented by using this probabilistic recursive Bayes filter to calculate this term, and then at every time step we just multiply them together. Or in reality we log transform and add because it's numerically more stable, but mathematically it's a multiplication of probabilities. And that's how we come to the Greybox parameter estimation from the state filtering problem. That's how those two topics are related. So this looks very nice. If you are used to probabilities and statistics, this is not terrifying mathematically complexity. But it turns out, unfortunately, in the real world, that things are never this simple. And for example, solving this integral, updating Bayes law here, or Bayes theorem, in order to compute this factor here is never as easy as this. Because it's in general not possible to find tractable mathematical expressions for all this. So we do have to resort to some sort of approximations, some sort of numerical computation schemes that are approximating this scheme. And for those who are familiar with Kalman filters, you might already recognize that the linear Kalman filter is one approximation to this. So in some cases, depending on how the system and the noise models look like, we can find actual implementations of the state filtering in various Kalman filter forms, which allows us to calculate this factor. So for the next few slides, we will now look at some different implementations of this state filtering problem. So of course we then start with the linear Kalman filter, which is the most familiar, I guess, example. And I will again be using this cleverly constructed robot example to highlight how the state evolution actually works here. So now, of course, the model is linear, like this. So we have our state transition matrix, the measurement matrix, and then we have the process noise as additive and Gaussian distributed. So it's random normal noise. And we have our measurement equation like so, where we have a measurement matrix multiplied by the state. And then in addition, some second random noise component, which is then the measurement noise. And it can be shown that if our system actually behaves like this, then the Kalman filter solution is the optimal solution. So as we discussed in the couple of slides ago, how can we balance the uncertainty of measurement and model? Well, the Kalman filter is the answer to that. If the system behaves as a linear system with additive noise, then the Kalman filter is the optimal balance between those two uncertainties. So how would this work? Well, we start with our initial guess, or guess at time k minus 1. So here we would have the posterior state and the posterior state covariance from time step k minus 1. And then we apply the model in order to do a prediction one step forward. And as before, we expect that doing a prediction with an uncertain model increases the uncertainty of the state estimate. So this covariance here is going to be larger than here. And that's actually quite clearly visible from these equations, that we, for any stable system, would increase this covariance. And as before, after the prediction step comes the measurement step, where this is the familiar Kalman filter equations, which shows that we have here a quite literal expression of taking measurements and previous states with measurement equation, and then trying to calculate the balance between how much do we trust the measurements and how much do we trust the model. And the difference between measurement and model is then literally balanced through the Kalman gain when we do our state adjustments or state update. So here we have a nice mathematical expression which sort of illustrates this idea that we need to balance the uncertainty between measurement and model, and we do that through the use of the Kalman gain. And the same is then done also for propagating the covariance. I will here not go too much into detail of the actual Kalman filter implementation. There are good sources for learning more about that, for example, in Dan Simon's book, Optimal State Filtering, or other sources around the literature and the web. But one thing which is interesting to note here is that if through this Kalman filter equation, if we set Kalman gain here to 0, so that this entire term disappears, that implies that our new state, posterior state, is actually the same as the prior state. And this results in ballistic simulation. So it can be shown that what we actually do with ballistic trajectory model fitting is run a Kalman filter where we force the gain to 0. And how does that happen? Well, the only way that the Kalman gain can be 0 is if we trust the model completely. So we say that the uncertainty in the model is infinitely less than the uncertainty in data. Essentially, that we have a perfect model. It's an interesting observation. So, in order to use Greybox parameter estimation in the linear case, it's actually pretty straightforward. We can recognize that this expression here, that's the evidence factor in the Bayes theorem up here. This is simply the multivariate normal distribution with this innovation process as the mean and the innovation covariance R as our covariance for this normal distribution. So here we can sort of calculate this directly, what this should be, and we multiply it together at every time step in order to form an objective function by using the Kalman filter. So I should note that there are schemes which does parameter estimation inside the Kalman filter, sort of augmented Kalman filtering. where we add the parameters to the state vector. And even though here we are talking about using Kalman filters for parameter estimation, we are not doing any kind of augment or dual filtering. We are running the Kalman filter exactly as it is intended by assuming the parameters are known, and then we run the Kalman filter all the way over our dataset, at each step calculating this factor and multiplying them together. And that forms an objective function. And this objective function is then used through numerical optimization or Markov chain Monte Carlo or some other scheme in order to come up with a new theta. And then we run the whole sequence again, calculating another objective function until we numerically obtain some parameter, which then gives us an optimal parameter estimate under the assumption of maximum likelihood. Now, of course, the world is almost never linear. Hence, this assumption of optimality in the linear Kalman filter is very rarely fulfilled. And therefore, it has been developed quite a lot of different variations of the Kalman filter in order to deal with these nonlinearities. And one less strict formulation of the state space model is this one, where we assume that we have a nonlinear state transition and a nonlinear measurement equation, but we still keep the assumption of additive Gaussian noise. And this could be argued reasonable using the so-called central limit theorem, which says that if you have a lot of factors that are random with some distribution added together, in sum they tend towards normal distribution. So one common way of constructing random normal numbers in a computer is just doing 20 independent draws of uniform random numbers and adding them together. And then they will in sum behave as if they were normal. That's a literal implementation of the central limit theorem. So we could argue that this assumption of additive normal noise is much more realistic than the assumption of a linear system, which is almost never the case. So this is a more useful formulation of the state space model. Now, one way to approach the problem of computing the Kalman filter for nonlinear systems is to reuse our previous slide linear Kalman filter, but by linearizing around some operating point, we calculate some approximation to this f and g in order to obtain these linear matrices A and C. We still use the actual model state and measurement equations for the states themselves, but we need these things for propagating the covariance matrices over here. So this line here and here could be implemented with the model as it is, but the propagation of covariance requires this linear algebra expression here, where we need this A, B, and C matrices. So that's why we need linearization. And this approach of linearization can be feasible at least over small steps in state space, which is why very often when we do this, we have to perform something called subsampling, which means that we do the prediction step many times for small steps before we do a measurement equation, or measurement update. So if we have long sample times between measurements, we might have to make multiple predictions before we can do a measurement update. And that's fine. The Kalman filter is perfectly capable of handling that. And indeed, this is a very common approach. So the use of extended Kalman filter has been well proven. It's been done a lot over the last, 50 years. So we know that this works. But it has some disadvantages that if the system is severely nonlinear, this approximation becomes unreasonable and therefore can give quite poor results because the approximation here is poor. So therefore there has been some interest to develop other types of Kalman filterings. First, how do we do Greybox parameter estimation on this scheme? Well, turns out it's pretty straightforward. We just do exactly what we did for the linear Kalman filter, except that we now have this innovation process and the innovation covariance as approximations instead. Because these C matrices are approximations. They are not, the system isn't linear, so you cannot obtain an exact C matrix anymore, but you cannot obtain approximation through computing Jacobians. So therefore this becomes an approximation, and hence the whole Greybox parameter estimation scheme is also an approximation. What can we do then other than the extended Kalman filter? Well, there have been several interesting ideas in the last couple of decades on how to perform or how to make Kalman filters that are better able of handling severe nonlinearities. And one such example is the so-called Unscented Kalman Filter. And the underlying idea here is that the extended Kalman filter tries to approximate a nonlinear transformation, that is the state transition and the measurement equation. And it tries to approximate both of those with a linear one. And the underlying idea of the Unscented Kalman filter is that if you have to do approximations, it might be easier to approximate this state distribution, which we assume is normal, with something else rather than how it's done in the Kalman filter, which is a mean covariance. So if we can approximate these distributions instead and use the state transition and measurement equations as they are, as nonlinear equations, that might be a better approximation to the underlying nonlinear system. And in the Unscented Kalman filter, we do this by calculating this so-called sigma points. So sigma points is a way of, through use of the Cholesky decomposition of the covariance, to calculate a specific number of these red points here, which somehow represent our previous state and the uncertainty of that state. And then we can propagate each of those points through our state transition model F. And then we can arrive at a new updated state, which is then a better representation of the real state and uncertainty than what we would obtain with linearization, for example. Another advantage of using Unscented Kalman filter is that we dispense with the linearization process, which means that the Unscented Kalman filter can be used on models that are not differentiable. Maybe it's not obvious when you look at the extended Kalman filter, but of course the process of linearization requires computing Jacobians. So if you want to do that analytically, you require a model that supports this. It can be where the derivatives exist. You can of course do numerical Jacobians also, but then you introduce yet another uncertainty or approximation through this numerical computation. But the Unscented Kalman filter has this advantage that it doesn't really need any linearization, and therefore we don't require our derivatives to be differentiable. Of course, there is much more to be said about the Unscented Kalman filter, so for that I refer you to the literature here, Julier and Ullmann's brilliant papers where they explain both the sigma transform and the use of those sigma transformations is in Kalman filtering. But for the purpose of our discussion here, it's just worth noting that we can approximate the linear Kalman filter using this unscented transform. And then from here, we can again calculate the mean and the covariance, which is what we need for our Greybox scheme. We can get the innovation process and the innovation covariance out of these equations. And as this example here shows, which was borrowed from one of these papers, the sort of ideal way of doing state transition is through what we call sampling or Markov Monte Carlo sampling. And in this example, it shows that if you have something here, which sort of looks like it could be reasonably approximated by normal distribution, if you put that through some nonlinear function, the result is probably not going to be normal distributed anymore, which both of these things sort of assume that you are always working with normal distributions. The Unscented Kalman filter has some tuning parameters that can be adapted to better represent non-normal distributions, but in general it's developed on normal distributions. However, we will in the later slide look at something called the particle filter, which is a better choice if you have severely non-Gaussian distributions. presentation. Just wanted to comment that, since it's sort of apparent from this figure that doing the sampling scheme like here, this is not really normal distributed anymore. So one further implementation of the Kalman filter for nonlinear systems is something called the Ensemble Kalman Filter. And this was developed by Geir Evensen in 2009 and further papers. It's a very interesting take on the Kalman filter, which sort of tries to introduce the idea of stochastic sampling, which is the basis of the particle filter, but still maintain some of the benefits of the Kalman filter. Just the first things to note is that in the literature surrounding Ensemble Kalman filters, they use slightly different terminology. So it's not predict update anymore. It's called forecast and analysis, which is essentially the same thing. But if you study papers on this, you shouldn't be confused by the terminology. That predict means forecast and update means analysis. It's the same thing. So the Ensemble Kalman filter is arguably similar to the Unscented Kalman filter in that we use representations of the state vector and we propagate those representations forward in time through each time step. So we don't do linearization, but instead we have a set of points which we propagate through the model equations. And then we do some clever mathematics to those in order to obtain the Kalman gain and do the adjustments with measurements and so on. And in that sense, this is similar to the Unscented Kalman filter. But there are two distinct differences with Ensemble Kalman filter and Unscented Kalman filter. The first is that in the Unscented Kalman filter, the way we choose the state representations is deterministic. Whereas in the Ensemble Kalman filter, it's stochastic, because we do Markov chain Monte Carlo sampling. So we draw random representations of states from the state space using some sort of initial state uncertainty, or initial state and uncertainty of the initial state. And that constructs an ensemble of state realizations, which is then propagated through time. And those state realizations are sort of continuously manipulated or perturbed in a stochastic way, which makes this ensemble always have this stochastic nature, that it's random in some way. Whereas the Unscented Kalman filter, the states are completely deterministic. We calculate the sigma points, we propagate them forward, we calculate new mean and covariance, and then we do the sigma transform again and again and again. And at every step, the new points are deterministic. There is no need to do any random number generalization in the Unscented Kalman filter, whereas in the Ensemble Kalman filter, we use a random number generator to perturb the states randomly. And another interesting observation is that in the Unscented Kalman filter, we calculate the mean and covariance at every step, and then we regenerate the sigma points through the sigma transform actually twice per time step. Whereas in the Ensemble Kalman filter, the realizations are maintained all the way through as independent state trajectories. So we don't redraw the ensemble at every step, but we keep them as independent trajectories throughout the whole data set as we do our Kalman filtering to obtain the innovation process and innovation covariance for parameter estimation. So we could say that it could look something like this, that the blue dots here would be the realizations of the state, which has been randomly drawn. We assume that the black dot in the middle here is our initial state guess, and the black ellipse is the uncertainty of that state. So then we would randomly draw a bunch of realizations. We propagate all of those through the model F, and then we end up with a new ensemble, which might look something like this, where all of these points here has a one-to-one relationship with a point here. So all of those points gets propagated through the model and then end up in some different distribution across state space. And we can then, using those points, we can calculate whatever statistic we wish on those points, because we can show mathematically that under some regulatory assumptions, these points are sort of distributed correctly in the state space to form an empirical distribution over the state. This is a table from one of my PhD papers where I'm comparing the Unscented Kalman filter and the Ensemble Kalman filter. So here we can sort of highlight some of these or illustrate some of these differences. So if you look at the table, you will see that the equations is fairly similar for the unscented and the ensemble Kalman filter, in that we always deal with an ensemble. We deal with some sort of weights in order to compute the mean and covariance. But where we have in the unscented Kalman filter, over here, we have this Cholesky calculations in order to deterministically compute new sigma points. We don't have such re-sampling of ensembles over here. And we see also that the noise, process noise and measurement noise covariances are in the unscented Kalman filter. They are added into the equations, whereas in the ensemble Kalman filter, they are added by random number generators and introduced into the state and measurement equations over here. So finally, what do we do if we are in this, if we have a system where the assumption of normal distributed noise is also no longer viable? If you have a nonlinear model and a non-Gaussian noise distribution, what do we do then? Well, then we can try something called particle filtering. And this is based on the idea of Monte Carlo sampling, which means that if you have some sort of distribution which you may not be able to compute, you cannot find a closed form expression, but you can sample from it. You can randomly draw a state, for example, and then you can try to calculate with that state and see how well it behaves, if it fits the measurements or not. Then you can do sort of a Monte Carlo sampling approach. And we can illustrate this idea of particle filtering using the same robot example. So now, as before, we start out at time k-1, where we still have a representation of our current belief. Where is this robot in the real world? So we have a belief on its state, which now is not represented as a probability distribution, which it was in the recursive filter. Neither is it represented as a mean and covariance, as it was for the linear Kalman filter. But now it's represented as an ensemble. So we have a set of possible states. And what tells us how probable a certain location is in the state space is the density of these ensembles. So you see here that there is one representation over here, one representation over here, and there is many more representations in the middle. So if we were to calculate or approximate this, for example, using a histogram, we would recover something which is similar to this probability distribution that we had in the first, the recursive base filter implementation. So, as before, the first thing we need to do is a predict step, where we take each of those states over there, which is our initial distribution, or the posterior distribution from the previous step, and we propagate them through time, through here, over here, the one time step ahead. And this is then done using the model, so we don't need any linearization here either. We just use our state transition model to calculate the best guess for what the next state might be, given each of those previous states or particles. And then for each of those particles, we do a measurement update, where we introduce this measurement, yk, and then we try to calculate a probability or a weight, which tells us how likely is each of those new states. Notice, actually, before we continue, that as before, the density of these realizations or particles has been sort of dispersed a bit here, because we use, as before, an uncertain model. So as expected, the density here is sort of less than it was here. We increase the uncertainty by doing a model prediction. And then we do this weighting scheme over all of these new prior state guesses. And we also do a normalization step here, so that they sum to 1 in order to be a proper empirical probability mass function. And then this next step in the particle filter, which we don't really have a equivalent for in Kalman filter, is something called a resampling. So from these here, which is our weighted prior states, that is the prior states from the prediction multiplied by the weighting scheme, which says how likely each of those states are, given that we now have a measurement which tells us something about where in the world this robot might be, we do this resampling. So with the probability equal to the weight, we choose the particle number I with probability equal to its weight. And then we generate the new ensemble, or the new set of particles by doing this resampling scheme. And these particles will then form our new posterior distribution, like so. And now all of the weights are again set equal, and you see now that the density is significantly reduced. Of course, this is maybe an exaggeration compared to a realistic example, but it's to show the case that through this inclusion of information, weighting particles, and then doing the resampling, we now increase our certainty as to where we are. That's natural because we added a measurement, so we would expect them to have a better idea of where the robot is located after we include the measurement than what we had before the inclusion of the measurement. And this idea of resampling can be thought of as spinning sort of a roulette wheel, like this here, where each of the particles is given a separate sort of pizza slice here, where the size of this slice is proportional to the weight. And since the weights have been normalized, they will always sum to 1 to form sort of a perfect circle. And then, of course, a particle here with a higher weight will have a larger slice, and therefore a higher probability of surviving into this new ensemble, or new set of particles, I should say. So if you want to use particle filters for Greybox parameter estimation, how can we do that? Well, we showed before that what we really need is this probability distribution here, which is this p probability of observing our new measurement y, given the previous measurements and a parameter vector. And we can show through marginalization that this can be represented as sum here, because we are now dealing with it's an approximation though, but we are dealing with discrete representations in state space. And therefore we now have a probability mass function which reduces this integral to a sum. And actually we find that the solution is this one over here. So this sum here, that's what gives us an approximation to this probabilistic entity or quantity here. So by doing this iteratively particle filter for every time step, and at each time step computing this sum over the weights, then we can notice this is the unnormalized weights. Then we can calculate our Greybox parameter estimation objective function, or the likelihood. So this can also actually be readily introduced into the Greybox framework. So this particle filter, of course, looks very nice. It's nice in general, and since it works on nonlinear, non-Gaussian systems, it's reasonable to guess, and of course it would be correct to say that they also work for linear and additive Gaussian noise systems. So it's sort of a general solution to the recursive base filter. But there is a reason why we still need the other Kalman filter approaches, because particle filtering has some distinct disadvantages as well. And one of them would be what is known as the degeneracy problem. So since we do this resampling scheme, which is actually required in order to utilize our computational resources more efficiently, if you had infinite computational resources, we would just have infinitely many particles, and then we would have an exact representation of the probability distribution, and we wouldn't need to do resampling anymore. But because we want these particles from generation to generation to have the maximum information content as to our current state, we do this resampling. But if by some chance we are in the situation where our prior distribution looks like this, that is the particles xk given information at time weight of k minus 1, so we have done a model prediction and we have distributed our particles like that. So it could happen that the model is really bad and it predicts all of the states, pushes all of the states to some location which has a very poor match with what the measurements actually say that the states should be. And this could then result in all of these states or particles over here being weighted to 0, and only a couple of particles over here that would survive the resampling into the next generation. And this would mean then that instead of, say, having n particles, we would have 2 particles repeated n half times. And that's what we call sample impoverishment or degeneracy, that we then really only have 2 points in state space which are represented in this particle ensemble. And that's not good, because then we completely lose ability to explore state space going forward. So there is a lot of literature and studies on how to sort of combat this sample impoverishment or degeneracy problem. For example, we can look at this effective sample size ESS here, and if under some conditions of this being below a threshold, we can do some random perturbations, for example, to redraw the ensemble, for example. But perhaps the easiest solution to understand is simply brute force, use more particles. As I mentioned, if we have infinite computational resources, we can use infinitely many particles, and then we would have, which would sort of solve the problem. Of course, that's not realistic in the real world, but if you have access to more computational resources, then using more particles helps to defeat the sample impoverishment problem. Some other implementational challenges with this. It can be difficult to decide how many particles to include in a particle filter. And that is sort of similar in the Ensemble Kalman filter as well, that it's difficult to set the ensemble size. In the case of the Unscented Kalman filter, the number of particles is exactly dependent on the number of states. It's the sigma transform which tells us how many sigma points we need in the unscented case. But for the particle case and also the ensemble case, there might be difficulty to decide how many points we need. Another issue is what we call the curse of dimensionality, which is that we are trying to explore state space using a limited set of realizations or limited set of particles. So obviously the higher the dimensions of the state space, the more difficult it is to provide an accurate representation of that higher dimensional space using particles. And in the Ensemble Kalman filter, this is slightly remedied by including some of the Kalman filter ideas, that we update measurements in order to guide the exploration of state space by measurements. But in the particle filter, this is slightly more of a problem. It's still an issue for Ensemble Kalman filtering too. A side note also here that in terms of sample impoverishment, that in the cases where the prior and the likelihood has a distinct overlap, then we tend to end up with this highly informative measurements situation, which causes sample impoverishment. This is actually an example of what we talked about in the previous slide, or a potential cause of that. And because of this, there have been many variations proposed over the recent years on how to deal with this. There are some good reviews I suggest you here, Kantas and Duché and Johansen, which covers a lot of the recent developments of different variations of these particle filters. So in summary then, for the purpose of computing a filtered state trajectory in order to do Greybox parameter estimation, we have many choices of implementation for the state filter or Kalman filter, particle filter. The simplest, of course, is the linear Kalman filter, which is very light. It's really fast compared to these other implementations. And this term here, this evidence term, can be computed readily using multivariate normal expression. If the system is only slightly nonlinear, we may use the extended Kalman filter in order to approximate the linear Kalman filter through Jacobians, and use basically the same expression here to calculate our conditional likelihood term. But of course then it's an approximation, because those state matrices is an approximation. For the unscented or Ensemble Kalman filter, which sort of are both for additive Gaussian noise nonlinear systems, we have the same expression of the innovation process and the innovation covariance, which is in both cases computed over the ensemble as expressed here. It's the same equations. And it's again, of course, an approximation, but this time we are approximating the distribution over the state using ensembles of realizations rather than approximating the state transitions or measurement equations by Jacobians. So in many cases, this is a better approximation. There's plenty of papers showing that this approach is beneficial to the extended Kalman filter in many cases. And there are some arguments also which show that they are always better, because even when this is a good approach, this would be at least as good as this. There are some papers discussing this also out in the literature. However, in the case where we have nonlinear systems and non-Gaussian noise, then the thing to do is the particle filter, which is then the heaviest computational burden. And then we have actually a very simple expression of this conditional probability, which is just the sum of unnormalized weights. Some references, if you are interested in further study of this topic, I suggest you to look at this list of excellent papers to learn more. That was a brief introduction to the interesting topic of Greybox modeling and the Greybox modeling framework, and how state filtering is important in that paradigm. I hope you found this video interesting, and I would like to thank you for your attention.